Greetings, this is Clifford Carnicom from the Carnicom Institute, and I'm continuing with a series of videos on a climate model, a software program that I worked on. And today's topic is that of aerosols, introducing aerosols into the model and some of the factors that are involved with exploring that aspect. So in terms of the layout, we won't repeat the tutorial from scratch, but basically the program is divided into two major components, on the left side being impacts of greenhouse gases and modeling that effect. On the right side, which we haven't talked about yet how to use, are a series of aerosols that have been set up for exploration. And now aerosols in themselves are a rather complicated subject and a little bit harder to pin down. There's a lot of uncertainty out there, and I think it would be important on the onset to describe that this is a model and that there are still certain uncertainties. However, as we speak today, we'll see that there are certain attributes of aerosols that can be identified, and in some respects those are arbitrary and unique enough to where the particular properties of a single aerosol, while that may be up for debate, the general properties of aerosols are something that we can at least get a handle on. So that's what we'll talk about to begin with. So this is the interface, but the more important topic right now is to discuss the general properties that have been incorporated into this model so that we know what we're looking for. And ultimately, the particular names attached to the candidate aerosols that are on there now are really not so important as an understanding of the physical properties we're looking at, and some of the difficulties also. So there's another graphic here that's being presented to you at the bottom. And this is how I have approached this problem. There's different ways I think that a person can look at this issue. This is a way that I'm looking at the problem, and that is there are two main factors that I'm looking at right now in terms of affecting the heating or the cooling ability of certain aerosols placed into the atmosphere. At this point, we're not talking about any of the ethical issues associated with this. We're not talking in detail about the consequences of aerosols. We're talking about, strictly from a modeling standpoint, heat exchange issues. And after we get that out of the way, then we can pave the way, hopefully for all of us, to begin to speak about those other factors which end up being really most important in the end, and this would be artificial means to regulate the environment and the consequences of those artificial methods and means. But let's not work with that right now. We need to understand how the model works and how we can explore it. So the two factors that I have looked at, the first is called the specific heat. Every substance there is has what's called a specific heat, and every substance is unique in its own right. It's a physical property of a characteristic, and what this characteristic measures, that's called a specific heat, and that's annotated by that symbol CP on here. That means specific heat at a certain pressure. But what this quantity measures is the amount of heat that is required to heat up a unit mass, a specified reference amount of mass. How much energy it takes to heat that up, that unit mass, by a specific, again, unit degree of temperature, namely centigrade or what's called Kelvin. So the units involved would be energy, and that would be expressed in joules in the physics world, and that would be on the numerator. Amount of energy per unit mass, so you'd have kilograms or grams on the bottom of it, and then you'd have per degree centigrade or per degree Kelvin. So these are the units that are involved with that. This is what it measures, a physical property of the relative amounts of energy that it takes to heat up a unit mass of various substances. That's an important physical property of everything, and I regard as being especially important in the world of examining aerosols and their effects. Now, there's another factor that's involved, because the specific heat is not really enough to capture some of what's happening that is important. And another dimension of aerosols is that of what's called albedo, or reflectivity. When you go about determining the specific heat of something, that's being done in a vacuum, that's being done in an isolated environment. It's not subject to, say, sunlight or something like that. And so specific heat doesn't capture the entire picture of what's going on. It primarily would be an additive thing, and it would always be a part of a whole in a additive fashion, and that's not accurate enough to represent what's going on. So reflectivity, or albedo, is another physical property that's very important in terms of trying to analyze heat flow. And albedo is a measure of what percentage of the incoming energy, in this case sunlight, is either absorbed or reflected. A low number means that it has low reflectivity. A high number means that it has high reflectivity. Gets a little bit tricky to keep this stuff straight. That's why I drew this graphic here to try and help us out, because you end up with a matrix here as a grid where we're working with two different variables. So high reflectivity, in contrast, would mean little absorption. If something reflects a lot of energy, then it doesn't absorb very much of that energy. And if something has low reflectivity, then it means it's absorbing that energy. So these are opposite ends of the coin here, but one of the same thing. So you need to keep straight, and I too have to keep straight on terminology and which direction you're headed on things. Okay, let's go back to that specific heat one. And as an example, if something had a high specific heat, that means that it would take a lot more energy to heat it up per unit mass than it would something with a low specific heat. It's a measure of amount of energy or heat that's required to heat up a unit mass. So if it has a high specific heat, then it takes more energy to raise that unit mass a certain temperature. And if it has a low specific heat, then it doesn't take as much energy to heat that unit mass up. So basically, things with a low specific heat will heat up more readily. Things with a high specific heat will heat more slowly, or actually in a relative sense, have a cooling effect. Okay? So two very important physical properties going on, and I have combined these in a way where I'm trying to get an estimate of their combined influence. And that's a bit of a trick, but this matrix that I presented for you shows at least the various factors that are going on, and that everything would find its place if we truly had knowledge of that. Specific heat is something that's very well known for pretty much every quantity. The albedo is a little bit more variable in terms of some of the information that comes out there, because it's a little bit more difficult to get a handle on. So I have estimates, again, that I'm using, but the important thing here in terms of presenting the scenarios that we're after is we'd like a representative substance that we know would be on the sort of the extremes of this grid at some point, so that we could evaluate that type of aerosol. In other words, if you had something that had a high reflectivity, something like a shiny metal, something that was highly reflective, okay, that means it's not absorbing very much heat, so it's going to tend to have more of a heating influence. But now you want to combine that. If you also had something that was high reflectivity and a high specific heat, then that would tend to be a cooling agent more than the converse. And this matrix shows that. Okay, something with a low specific heat heats up quickly. Okay, so therefore it gets warm quickly. So you see that one down here in the bottom. Okay, and also if that same material absorbs the heat or basically has low reflectivity, then it's down in this corner and it's more of a heating agent. So you see in this graph, these are the extremes on the lower left here of things that would be heating of a heating nature, and things at this end would be those of a more cooling nature. So to test this kind of problem, you'd want some type of representative substance of these, and that's what's important down the road. Whether or not the actual numbers attached to each one ultimately will be correct, I'll keep working and settling on that, but we're after that influence, and I've tried to choose what I think are some representative agents to work with. And then in the center there, you basically have a balance point, and then on these two ends of the matrix there, you have combinations. You see it's a combination between both of them that can go either way, and one of them could be more dominant than another, and those are obviously more difficult to determine. And this is why one of the reasons I think there is so much uncertainty about what the impact of putting aerosols into the ground is. You'll find one paper that says it'll cool it down, you'll find another paper that says it heats it up. So there is a lot of variability here. I've tried to do my best to come up with representative candidate descriptions inherently in the program. Now there's another thing mentioned here at the bottom, and we want to keep this in mind too. Not only do we have these two variables going on, but in our minds at least we want to keep track of the fact of where something is. It makes a very big difference where something is located. If something is highly reflective of energy, the albedo is very high, well, the way that that affects the Earth is totally different if that material is in outer space or it's right next to the Earth. So the location of things is very important. In fact, that came up in the Teller arguments, that many people were claiming that things were automatically being cooled by putting aerosols into the ground. But when you read Teller's paper, you saw that he was literally setting up his systems in outer space. He had 3 places total where he was putting those aerosols into the upper regions, and 2 of them were in outer space, and 1 of them was in the extreme higher portions of the atmosphere, basically stratosphere. That's a totally different story than whether or not these aerosols are down closer to Earth. So where they are is another important factor to keep in mind. Now, the next thing that we should do to establish a framework is understand that what we're really looking at here eventually are, first of all, differences. We're looking at changes, and anytime we have a change, we want that relative to some kind of reference frame, some kind of standard. What I have done, and what's shown itself to be most relevant in this model, is to look at these particular aerosols or particulates or materials, whatever, put into the atmosphere with respect to air. In other words, you're after finding out whether it has a heating influence relative to that of air. Remember, air has a specific heat. Everything has a specific heat. Air has a specific heat and a level of reflectivity associated with it. So we want to know the difference with respect to that air, and so this is what we're actually looking at as I've tried to quantify that, is what is the impact of a various aerosol form relative to that of air. Now that we understand the factors that are behind the scenes in terms of impacts and that are driving aerosols, let's go back to the model and let's start playing around with a couple of examples. And today we're going to restrict ourselves just to the right side of the model in terms of exploring aerosol combinations. And what gets interesting, and later on we're going to have another video here where we'll start to combine them more. I'll probably have a little bit of combination here today, but we're really going to just focus on these right now, and then have another series, another video where we talk about combining these things. Again, this is not the subject of health impact or consequences to the environment. That's another whole subject, and I hope to get to that. But we're just after learning sort of the modeling system here at this point, so that it can be explored, with thought and intelligence, basically, and design as a learning environment. Okay, now on the right hand side we have 9 quantities that have been given to us. I have attempted to quantify and characterize these in a combined sense, and that's a little bit tricky here, to combine both of those factors into some coherent fashion. And I've chosen a method here that'll be described at some point, but basically it's a regression involving those 2 variables to give in a sense, what's called a modified specific heat is what I'm using to reflect the incorporation of albedo or reflectivity. So there's an attempt to do that. Later on, like I say, maybe these numbers will change, but the fact is they're not all the same, and we can at least start to explore the differences. And what I'll do is I'll guide us through sort of the ranking of these things as they have appeared thus far. And I don't see that list right now, but yeah, there's the list. Let's take one of these at a time. Carbon black. Most of us have an idea of what carbon black is, like soot. And it's really interesting. You can find papers that will say that carbon will cool things down, and other papers that will heat things up. So again, it becomes difficult to sort out. I'm adopting a model right now based upon these physical properties that I'm describing that lead to a net effect of heating increasing with carbon black. Remember, where you put something is important. Putting soot on snow causes an immediate effect. Putting soot in the stratosphere would have a different kind of effect. But nevertheless, we're trying to talk about a representative environment. I've chosen mid-altitude to try and describe this model. Roughly about 15,000 feet is where things are generally being staged. But if you were to introduce aerosols of a carbon black nature, okay, and I've actually tried to be realistic with all the units here. There's been a lot of work in terms of scaling the influence of these. It's actually coming together quite nicely, and there's interesting interpretations about this also. But if you notice here, this is in a range of values that we're dealing with is in micrograms per meter. That's very interesting, as we will see, because that range is right at the level of the environmental pollution laws. So there's another topic to talk about there. But the numbers are starting to be realistic. Namely, 25 to 50 micrograms are in the range of air pollution laws. So let's say we put some carbon black in there, and now we need another factor here. And we mentioned this in the introductory tutorial, but how many times you do something. The first slider up here represents how much mass you're putting into the atmosphere as a whole on a particular, say, operation. The number down below is how many times you do something, because this obviously has an accumulative effect, and that accumulative effect would be important to consider over time, especially when you're dealing with health and environmental issues. So this is another variable, how much you're putting into the system and how often you're doing it. So let's just boost this stuff up, roughly 2/3 into each system, and let's see what it does. And what it does, we see it starts to introduce a heating effect. Okay, this is what my numbers would show at this time in combining both the absorption. It's black, so it tends to absorb more energy, and the specific heat is less than air, so it heats up more. By the way, we'll see that metals generally have a lower specific heat, so most metals are going to heat up the atmosphere. So that's a general property we will look at. We're going to find that water and ice will tend to have a cooling effect, and this makes sense from our intuition that when it rains it cools things down. And one of the reasons for that, a very strong reason, is the specific heat, the nature of that specific heat. But we see that we picked up some heating. It's fairly mild, but we did pick some up. Now, notice that I don't have any of the greenhouse gases into this picture yet. So one of the reasons that this number will stay low is because it's not tied in this mode. This number will stay fairly low because it's not tied in with any greenhouse effect. I'll go ahead and introduce this because there is a relationship, as we have described, whether it's not an issue of causation, but there is a correlation between increase in temperature and increase in greenhouse gases. So stepping aside from the issue of cause, what will happen here is if we start to introduce a little bit of CO2, you're going to start to see that rise quite a bit. Okay, that's because that CO2, that increase in CO2 gas, is having a significant effect on the atmosphere. So right now what we're doing though is we're going to ignore the influence of greenhouse gases, and we just want to see the direction, the general direction, and some estimate of magnitude, relative magnitudes of how these various aerosols are expected to behave. So I'll boost these things up to the high end of the scale so we can start to see what do we think their effect is going to be. So the carbon black, we'll see, has a presumed, everything is presumed at this point, but it's based upon, you know, fair reasoning, I think, has a heating effect. Let's step through each one. You can hit the reset button as you understand to get things back to 0. Okay, and we'll step through each of them. Now aluminum, there's actually 2 on here that are exceptions. Most of these will have a heating effect. The net effect of most of them, the majority of them, will be a heating effect, as most metals are. 2 of them will be the other direction, and 1 of them appears to be almost neutral. Let's go to aluminum. And there's different forms of aluminum. There's so many variables here. Okay, I'm just choosing something to get us started. You'll see here that you have a mild cooling effect. And now the rationale for that is that shiny metals are generally going to be more reflective. Okay, and you're going to find that the specific heat of that substance is pretty close to air. It's a little bit less, so it has a mild heating influence, but it's also a reflective type material. So the net effect, again, it's a little difficult to absolutely know what the net effect is, but I have come up with my own model for trying to estimate that. We see that the net effect of introducing carbon black, and we'll call this at mid-level altitudes right now, but roughly 15,000 feet is again the general model that's here. Carbon black is positive or heat inducing. Aluminum would be negative. Okay, and honestly, if the numbers refine themselves and I change that, that'll be fine, but it's a reasonable start that we can make an educated guess, and it's not just a guess, there's a regression, planar regression in this to try and estimate this. Okay, sulfuric acid, let's just step through each one of them quickly. Sulfuric acid shows itself on the heating side. Okay, at this point there's different forms of that. There's a question about sulfate, whether something is an ionic form or not is totally different than whether it's solid. Sulfate ions are a fascinating topic that I'm starting to pick up on. They may be very unusual with respect to their heat properties. Sulfuric acid, again, we're going to skip the environmental parts of this for right now. Let's just get on to see what these are. Now, the numbers on these are not all the same, and you'll see that even though we're dealing with no additional heating from the greenhouse gases. The case of thick low clouds is an interesting one because it stands out. It stands out as being a little bit stronger than the others by magnitude. If you compare that magnitude, it'll be a little bit greater than the others. And that's because if you look at what's happening with water vapor, that specific heat is extremely high. It's quite unusual. Air is close to 1, and water vapor is close to 4. That's a very large number for a specific heat. So that has a very strong cooling effect, which makes a lot of sense from an intuitive standpoint. Now, so the influence from water, again, where something is important, because if it's lower to the earth, it's more likely to be in liquid form. If it's higher up, which we'll get to in just a second, it's likely to be ice, and that's different. So let's work our way there. Barium has a very low specific heat. It's like 0.29 versus 1. So that means that that type of material is expected to be a pretty strong heating influence. And I'll mention that I made a model many years ago. It's static in terms of its presentation on the site, but that was a model that started to examine the question of barium, and that's where the conclusion was made that the net effect of that was increasing heat, and that that magnitude of that impact is on par with that of global warming. It's very interesting, returning to the problem several years after, that the results of this model, which have been done really completely independent from that, the consequences of this model that's been developed are really perfectly in accord with the work of that earlier global warming model that I had created. It's quite interesting. This one is obviously much more dynamic, but it is interesting that this model is showing the same types of results. Barium has a very low specific heat, so it's expected to heat things up. The albedo, it's the more extreme cases on albedo that are easier to determine, such as carbon or a shiny metal. In between, the effect of it is less, and that's why this is dominated. The reason that barium is heating, it's dominated by that specific heat quality to the metal. Okay, so that's that one. And okay, now we have a very interesting thing on clouds. We've talked about low clouds. There is a difference in the way that clouds behave between whether they are low and thick, basically our rain clouds, or whether or not they're very thin and high. And it's an interesting determination that has come to light in this recent work, that not only are these particulates increasing the heat and causing the formation of, quote, thin high clouds, and that's a whole topic of research that's been presented over years, but high clouds in themselves, thin high clouds in themselves, of and in themselves, are heat inducing. This is a very, very interesting observation. So the claims of global warming are very, reducing global warming by having that thin high cloud layer are actually very hard to justify at this point. You have two reasons right now that aerosols in the upper atmosphere, the upper troposphere here, are likely to be heat increasing rather than decreasing. One would be the nature of the materials. If they have a specific heat less than 1, then they are going to be increasing the heat, and the fact of how water behaves excuse me, water behaves in an ice form. The specific heat of ice is lower, quite a bit lower than that of liquid water, so it doesn't have as much of a contribution there. So there is an important distinction between where clouds are and whether they are ice or water, and whether they are thick or thin in terms of their impact upon the heat exchange. So when you see the clouds that directly result from aerosol operations, we can be fairly assured that they are indeed increasing the heat quotient rather than decreasing it. Now another thing, this is more of a use of the model rather than getting through each one, but what's actually would happen there if you had high clouds, the reason for that is you're going to have a aerosol that goes along with it. The aerosol is acting as the condensation nuclei for those, quote, high clouds to form. So the truth is, something like this is more likely to go hand in hand as you're experimenting with the model. So it would be quite a reasonable thing to introduce a particulate material along with the formation of those clouds, and you're going to find that you're going to get a greater effect. You're going to get a greater effect than just the one by itself. Okay, ash, you can again set things to 0 anytime you want there, and volcanic ash is also on the heating. Remember, the majority of these have an apparent heating effect from my analysis, and 2 of them were reversed, between aluminum expected to be reversed and the thick low clouds expected to be reversed. So volcanic ash came out on the positive net side. Magnesium comes out to be, from my work, almost just neutral, as can be. The specific heat of that is almost identical to that of 1, and it tends to be probably on the reflective side. So where something would be placed would be probably a bigger factor there, but that comes out to be almost neutral at this point. And that shows that when you combine them together in the way that I have. And strontium is on the same general class as barium. Is the specific heat of that is very low, and so you expect to have a likely heating impact from that. So this steps through each of the different aerosols that are being here given as examples. They're sort of like representative samples of what to work with. And over time, we will play with various combinations of these. And as an example, if somebody were to introduce a positive effect, then we could start to ask, well, is there something that might serve as an offsetting influence? Let's pick one of those examples to get things going. Let's say that we did now start to introduce a little bit of CO2, so we start to see how these interact. Now, CO2, let's back up to the other side. Let's pick something like carbon, and let's introduce some of that in a fair quantity. Okay. Now that effect by itself we've seen is fairly small. It's there, but we can pick up that it appears to be a heating effect. But there's no contribution coming from the greenhouse side yet. Now let's go ahead and introduce that, and be good to keep track of that number. But let's go with even just a moderate level there of CO2. And you'll see a dramatic increase. So what you're seeing here is that the combined influence of now both of these, because it is much greater, because see, now you're providing a source of energy. When you introduce the CO2, we know by a process of correlation that the temperature of the air is going to be higher. We know that correlation exists. So therefore you're now going to have a source of heat for the aerosols. And that quantity that we talked about of specific heat is actually going to be employed. It's going to be utilized because of that source of heat. So the contribution of both of these together is a more powerful impact than either one by themselves. So let's run through one of numbers where we start regulating it. And we'll run through that as one scenario, and that'll set the stage for you to explore various combinations in the future. Let's go back to 0, and let's build it up. Let's start by introducing a net positive heat-inducing aerosol into the atmosphere. Let's keep track of our numbers here a little bit this time. Let's reset this one to 0. Everybody's reset except for that one. And there's our number, okay? And so that's a positive 0.06. We'll keep track of these variables this time. It's a positive 0.06%, and time is one of the most interesting things. And we see that we're dealing with 1160 years to raise that 1 degree centigrade. We've talked about this in earlier videos. That's our frame of reference right now with that introduction of the particulate. Now let's put in a modest level of CO2. And I'll go with 1.5 this time. Right now, let's put that in there, and we have a very big difference that takes place with their combination. We're seeing we're up to 0.84 now, 0.84, and our time is now dropped to 82 years. So that's a huge impact to the system there. Now, let's play with offsetting influences. Two things are building things up right now. We know from previous work on the greenhouse gases that I could play with the methane to serve as a counterbalance. But this time, let's start playing with the aerosols. And remember, I don't have but 2 on here that are candidates for doing this right now. But water is a simple one, and a fairly obvious one to consider. Let's start to see if I can start to balance this or not. And I may or may not have enough, and if so, we will diminish. Yeah, it's still, I'm going the wrong direction because water has a net negative influence. That was a great observation there. Let's see, something didn't make sense. Water has a net negative impact upon heating when it's low and thick, rain clouds basically. So sure enough, see, there it is, dropped it down right away. That was a very good example, and let's try and see if we can get maybe just a little bit closer to that cooling point, and it's still cooling it down, so let's bring it down a little bit. Right, okay, I crossed it over, so it's somewhere in between, and you'll see that balance point is going to be in here somewhere. I need a little bit more. I'll try and pick it up, but hopefully you see the idea here. You're after finding that, yeah, it's very close there, right? Finding that balance point, and here's what's happened is now you have a, there it is, it's coming in there. You have a scenario that's using 3 different factors to produce a net neutral effect, but it is a combination of, there it is right there, it is a combination of introduction of a particulate to begin with, aerosol, increase in a greenhouse gas, and understanding the value of water on this planet and how our choices for cooling things down seem to be a lot more difficult basically than heating things up, but we exercise that option here. We understand that if we had that aerosol in there, we're likely to have an increase here, so we could play with that. We also know that we've learned about the offsetting influence of decreasing methane, so basically any combination that we want to reach here can be achieved from a theoretical standpoint, no matter sort of how complex the arrangement. And we'll save this discussion for another time, but this now starts to open the door towards the artificial manipulation of the environment, the means to that. For those that question the means to do this, I think that we would have to be ignorant at this stage to not understand that these types of relationships that I'm showing in this model are known, they are understood by those that have the means to influence the health and environment. And I'm not going to bring up all the ethical issues, but certainly one of the main things that's different when we flipped over to the aerosol side today and we started introducing that, that is not a neutral affair. The entire story here is not just one of heat. Heat is the way that this model is examining things. But with any introduction of any material into the atmosphere, you have a consequence to it. Okay? There is an effect to it. There's all types of different ways to have an effect, and they've been written about for years, whether it's going to be health, whether it's going to be general visibility, whether it's going to be impact upon the environment and toxicity. There is a consequence of putting aerosols into the atmosphere, and as we said, many people can't even settle which direction they think something is going to go. There are applications. There are things that you can do as a result of putting various particulates into the air. I've talked about that for years, electromagnetic properties. So we can see that, number one, the question of whether situations can be managed, whether are to our detriment or purported benefit. The fact is, this model shows that it very clearly can be done. But once you show that it can be done, you must start examining the ethics and the consequence. And that's really the purpose of this, is to make the case and understand that yes, we can do this. But the real purpose of this work is to demonstrate that as a consequence of making any type of changes like this to the environment, you must now deal with the ethics, the morality, the legality, and the impacts upon environment and health by making those changes. And obviously the lack of consent or involvement of the global population in such maneuvers is a travesty of the highest order. So I will attempt to stick to the modeling and technical basis here, but we do want to understand why this work is being done. It's not just a technical exercise. It is to make the case that it is understood, it is not ambiguous, that artificial regulation of the environment can take place with respect to introduction of various components into it from a heat standpoint. And we can have the debates about climate change and global warming. We can have those debates. But those debates are missing the real impact of what it is we're talking about here, and that is the deliberate injection of foreign substances into the atmosphere and the consequences of those foreign injections and their impact upon health and environment. So that's where the conversation will need to go, and hopefully this model will prompt you to start raising those questions and to seek accountability for changes that have obviously taken place in the environment. I think on the last video there we may consider the combination of things in a more combined sense here, but enough is on the ground here in terms of the discussion of the model to hopefully aid in your understanding of how things can be done, and then raise the bigger question about what do you intend to do about letting it be known that such things are almost certain to be in place, and all the evidence shows it is being done, and the ethical and moral grounds for the discussion that is required by us as citizens of the planet. So thanks very much for your patience and willingness to hear me out in terms of the technical aspects of this. But hopefully we have eliminated certain ambiguities about what might be possible and what is possible, and we can get on to the bigger issue of the rights of citizens to be involved in the welfare of themselves and the planet. Thanks a whole lot. Have yourself a great day, and I'll talk to you again as the occasion arises here. Bye-bye now. This is Clifford Carnicom from the Carnicom Institute. Greetings, this is Clifford Carnicom from the Carnicom Institute, and I'm continuing with a series of videos on a climate model, a software program that I worked on. And today's topic is that of aerosols, introducing aerosols into the model and some of the factors that are involved with exploring that aspect. So in terms of the layout, we won't repeat the tutorial from scratch, but basically the program is divided into two major components, on the left side being impacts of greenhouse gases and modeling that effect. On the right side, which we haven't talked about yet how to use, are a series of aerosols. The important topic right now is to discuss the general properties that have been incorporated into this model so that we know what we're looking for. And ultimately, the particular names attached to the candidate aerosols that are on there now are really not so important as an understanding of the physical properties we're looking at, and some of the difficulties also. So there's another graphic here that's being presented to you at the bottom. And this is how I have approached this problem. There's different ways I think that a person can look at this issue. This is a way that I'm looking at the problem. And that is, there are two main factors that I'm looking at right now in terms of so the two factors that I have looked at, the first is called the specific heat. Every substance there is has what's called a specific heat, and every substance is unique in its own right. It's a physical property of a characteristic, and what this characteristic measures, that's called a specific heat, and that's annotated by that symbol CP on here. That means specific heat at a certain pressure. But what this quantity measures is the amount of heat that is required to heat up a unit mass, a specified reference amount of mass. How much energy it takes to heat that up, that unit mass, affecting the heating or the cooling ability of certain aerosols placed into the into the atmosphere. At this point, we're not talking about any of the ethical issues associated with this. We're not talking in detail about the consequences of aerosols. We're talking about, strictly from a modeling standpoint, heat exchange issues. And after we get that out of the way, then we can pave the way, hopefully for all of us, to begin to speak about those other factors which end up being really most important in the end. And this would be artificial means to regulate the environment and the consequences of those artificial methods and means. But let's not work with that right now. We need to understand how the model works and how we can explore it. That have been set up for exploration. And now, aerosols in themselves are a rather complicated subject and a little bit harder to pin down. There's a lot of uncertainty out there. And I think it would be important on the onset to describe that this is a model and that there are still certain uncertainties. However, as we speak today, we'll see that there are certain attributes of aerosols that can be identified, and in some respects, those are arbitrary and unique enough to where the particular properties of a single aerosol, while that may be up for debate, the general properties of aerosols are something that we can at least get a handle on. So that's what we'll talk about to begin with. So this is the interface, but the more